So welcome to this video on dark matter, and in this video I will tell you about a brief history of the dark matter, what its role is in our universe, what it may be, and how we plan to find out more about it. So in 1933, Fritz Zwicky was studying the Coma cluster, a large supercluster containing more than 1,000 galaxies and 300 million light years away. He noticed something odd. Some of the galaxies were moving so fast that they should have escaped the gravitational pull of the cluster if the luminous matter was all there was. He postulated that there had to be a much greater amount of dunkle Materie, or dark matter, than normal matter, in order to explain these large velocities. This is the first recorded mention of one of the greatest mysteries of the universe. Then, in the 1970s, Vera Rupin also stumbled upon an oddity. While measuring the rotation curves of spiral galaxies, she found that instead of the expected decline as you get further from the center, the curve remained flat. Stars on the outer edge of galaxies rotated with the same speed as those near the center. She estimated that this would require 5 to 10 times as much dark matter than regular matter, and that the galaxy be embedded in a dark matter halo. Such a dark matter halo would have to be many times larger than the galaxy it surrounds. During the 1980s, several alternative explanations were proposed. Most famous among them was modified Newtonian dynamics, which tried to do away with dark matter and instead modified our understanding of gravity on larger scales. It worked well for dwarf galaxies, but failed completely when applied to galaxy clusters. Dark matter remained the best explanation for the observations. It is believed that dark matter is responsible for the large-scale structure of our universe. After the Big Bang, there were some fluctuations in the otherwise uniform distribution of matter, as seen in the baby picture of the universe, that is, the cosmic microwave background. These fluctuations led dark matter to start to collapse into larger structures, as seen in this simulation. The cosmic web of filamentary structures is evidenced in large-scale surveys like the Sloan Digital Sky Survey that measured the positions of thousands of galaxies. Current models suggest that it is the dark matter that provided the seeds for galaxy formation, and where the filaments connect or cross each other is where the large clusters of galaxies, like the Coma cluster which Fritz Zwicky studied, form. The simulations that recreate the conditions we see today only work when dark matter is included in their models. There is also evidence of it through mass measurements of large structures, and the Bullet cluster is a fine example thereof. Here we see that the normal matter and dark matter don't interact. This image shows two smaller clusters passing through each other, and all the gas in them have collided and been concentrated in the center, while the stars and the rest of the mass, including dark matter, has continued unhindered. So, what is this dark matter made of? Well, among the things we know are, it doesn't interact with electromagnetism, it has to be stable, and it has to have mass. We know it doesn't interact with light or magnetism, as we have noticed this by now. It's everywhere, even flowing through you in great quantities at this very moment, yet we've never seen a dark matter particle interact with light or magnetism. We know it has to be stable, as it was most likely created in the Big Bang with the rest of the energy in the universe, and since we still see the effects of it 13.8 billion years later, it has to be stable at this timescale. Finally, we know it has to have mass, as it's through its mass and hence its gravity that it interacts with its surroundings. The main candidate is called a WIMP, that is, a weakly interacting massive particle, an example of the creativity of physicists when naming new things. As the name implies, it interacts very weakly or not at all with normal matter, and it has mass. While no such unknown particle has yet to be discovered, it is the prevailing theory as it agrees with observations. There is another candidate which attempts to explain the excess gravity, or mass, without modifying what we currently know about particles, encapsulated in the standard model of particle physics. This theory goes by the name of MACHO, that is, Massive Astrophysical Compact Halo Objects. This theory only uses known physics, such as black holes, neutron stars, brown dwarfs, and other such astrophysical objects to explain observations. While mostly discredited, it still has some proponents among today's astrophysicists. A final candidate I have to include as a student of the Niels Bohr Institute and fan of Holger Bech Nielsen is Holger's proposed dark matter balls. Holger, along with Colin Froggatt, proposes that dark matter might be made up of centimeter-sized objects made from condensates of highly compressed ordinary matter bound together by 6 top and 6 anti-top quarks. These balls are suggested to weigh around 100 million kilograms despite being no larger than a marble. Which of these theories are correct is something future physicists, maybe even you, will have to determine. Currently there are two types of experiments underway to try and learn more about dark matter, the first of which is direct detection. Two such experiments are the Xenon 1T in Gran Sasso National Laboratory in Italy and LUX, the Large Underground Xenon Experiment in the Homestake Mine in South Dakota, USA. Both these experiments hope to detect WIMPs using large quantities of liquid xenon. The basic principle is that they hope that a WIMP passing through the large tank will interact with a xenon particle, and that will cause it to emit some light, which will be picked up by sensitive sensors in the tank. Both of these experiments are located deep underground to provide as little background noise as possible. Cosmic rays and radioactivity from many different sources could confuse the sensors, so by going deep underground there is a natural shielding from many such sources of noisy data. The other method in use to try and learn more about dark matter is indirect detection. With this method, gamma-ray observatories such as on the Fermi satellite is used to survey the sky for signatures of dark matter annihilating or decaying. This means that if dark matter has an antiparticle, like normal matter, such particles may be created in high-energy events in the universe, and if it meets its normal partner, it may annihilate like ordinary matter-antimatter would, sending out radiation, which could then be detected. Some models also suggest that dark matter could decay from one dark particle to other dark particles, and again releasing gamma radiation. Such surveys of the sky have to eliminate all the ordinary sources of gamma radiation, and as such will become a difficult but possibly fruitful task. The Cowley Institute for Particle Physics is heading up one such survey. So, to sum up what we've learned, there is a great mystery in our universe. There is some gravitational force that our current understanding of the universe cannot explain. Galaxies and clusters move too fast, galaxies themselves rotate too fast, and there is more mass in large structures than can be accounted for by stars, gas and dust. We see the cosmic web, and simulations cannot recreate this structure without including dark matter in their models. Current explanations of dark matter are that they are WIMPs, machos, or maybe even dark matter balls, or indeed maybe none of the above. Experiments are underway using direct detection like the Xenon 1T and LUX, which hope to see interactions with xenon in large tanks underground, and there is also experiments hoping to see gamma-ray signatures from annihilation or decays of dark matter. I want to thank you for watching, and I hope you've learned something about this great cosmic mystery that is dark matter.